So now I want to conclude our introduction to Fourier inversion theorem by some L2 theory. If you recall, in the classical harmonic analysis, there's a nice theorem called the Plancherel theorem. Basically, it tells you the L2 space on the unit circle is the same as the L2 space on the set of integers. So they are isomorphic as Hilbert spaces, and how you move from one to the other is by this Fourier transform. So you take F mapped to the F hat, that's going to be a unitary operator between these two Hilbert spaces. And now we have all the tool to extend this theorem to the more general locally compact abelian groups. So here's the theorem. So suppose I have our Fourier transform only defined on L1. So right now we don't have it equals L1 equals to L2 because our G may not be compact. So let's just say let's only define on L1 intersect L2. Well, I will map it to something F hat. Well, when I do the F hat, well, there's no reason to believe this F hat is inside L2. Well, but this theorem tells you the F hat is actually this image is inside L2. And the left-hand side, is going to be dense in the L2 of G. So if as long as you have something that's isometry, then you can extend uniquely to some isometric operator between these two Hilbert spaces. Well, on the left, you do the completion, you end up as an operator on the L2 of G. On the other hand, you have the L2 of G hat. So it turns out this Fourier transform can be extended uniquely to a unitary operator, not just isometry, but also unitary. So because here everything is Hilbert space, a unitary essentially just means an isometry that has a surjection. Okay, that's also a surjection. So another way of saying that is this unitary preserve the inner product. Okay. All right, so let's try to prove this fact. All right, so first of all, I need to show that this Fourier transform indeed maps L1 intersect L2 to the L2 of the dual group. So let's take an F inside L1 intersect L2, and let's consider the following function. We've seen this several times already. So you consider the F convolute with its own involution. And because your F is inside L1, and so its involution is in L1, your convolute, that's still in L1. But the nice thing is that whenever you do this, you end up with inside the pos-definite ones. Okay, so this one is certainly inside the B1, so you can apply the Fourier inversion theorem. So, and we also seen this trick several times. So if you consider its Fourier transform, we show the Fourier transform when you kind of preserve the Banach star algebra structure. So this one is just going to be equals to the F hat, the entire thing norm squared. Okay, so we have seen this trick already. So now we can just rewrite everything using this Fourier transform and this Fourier inversion to connect the L2 norm of F hat with the F. Okay. So how do we do that is that if I consider the integral of the F, the 2 norm of the F, okay, so this is df, fx dx. One way of looking at this is that this is essentially just the integral of fx with the f of x inverse, but then you do the check, okay? And then, so here the f check evaluate at x inverse give you the f of x bar, okay? All right, so but this one, if you look closely, you treat f and f hat as two L1 functions, essentially just integrating f of x against f check of x inverse. So this is, by definition of the convolution, this is the convolution of these two functions evaluated at the identity. Well, now you have f convolute with f check, that's inside the B, so you can apply the Fourier inversion. So by the Fourier inversion is given by the integral of its Fourier transform. So let's do the whole thing. Fourier transform evaluate at some character phi, and then you integrate phi of the identity here. I'm at identity now, and then you do d phi. So d phi is the dual measure on your G hat. And you may notice one thing. So first of all, this phi of E, because E is the identity, this one is always equal to 1. And we also proved that when you do the Fourier transform of this f convolute f check, you get the norm of the Fourier transform of f squared. So this is just the integral of the f hat, the whole thing squared. Okay, of course, evaluate phi. Okay, d phi. So this essentially just proves the L2 norm of the f is the same as the L2 norm of the f hat. Okay. So essentially, I prove the f hat is inside L2, and moreover, this is the map f to f hat is an isometry. Okay, so it's an isometry. So now, essentially, I just need to prove this one is going to be unitary. Okay, because once I have isometry, I know it's bounded. I can extend it to the L2 of G by the continuity. So let's just show as surjection. Okay, so I need to show this f is surjective. All right, so if it's not, well, then, of course, because we're now living in a Hilbert space, the good thing about Hilbert space is that if your range is not surjective, well, then it just means, well, you can have a perp, okay? So if there's a perpendicular space, basically when you integrate against that space, you always get 0. So let's let some say psi is inside the L2 of G hat that's living inside the perp of the range. Okay, so let's say psi is perpendicular to the range of the L1 intersect L2, the Fourier transform. All right, so what does that mean is essentially the following. So if I take any x inside G, and then let's take any f inside L1 intersect L2, then what I have is that if I integrate this psi of x against the, I shouldn't say psi of x, I should say psi of phi, because I'm integrating on the G hat. If I'm integrating against, let's say I left translate the f, and then I do its Fourier transform, okay? So of course, because I'm taking in the product, and I need to take the conjugate, evaluate the phi, and then d phi. Because they're perpendicular, this inner product has to be equals to 0, okay? Well, so now let's do some side calculation. What is the Fourier transform of the left translation? Well, let's just quickly do that. So if I have Lxf, Fourier transform evaluate phi, so this is just equals to the Lxf evaluate, say, y, and then I have a phi y bar, and then I do the dy. And then the left translation is just f of x inverse y, phi of y bar dy. dy is the Harmonic measure, so you can use the translation invariant. Now it becomes the f of y, so you multiply y by x, so the x inverse get cancelled, but then you need to compensate here. The phi becomes phi of xy, and now because x is going to be a constant, you can put a phi of x bar outside. Okay, so this is become the phi of x bar, and then you do the integral of the rest, which is the Fourier transform of f. Okay, so essentially, when you left translate something, its Fourier transform is just multiplying this phi x conjugate. Okay. All right, so now we have that. So let's just plug into this formula. So now I know that this integral of psi of phi, and then I have phi of x, okay? And then because I have a bar, so this bar got canceled, and then I have this f Fourier transform of f phi. I need a bar here. All right, so this one is always equals to 0, but because now this phi is, I'm integrating against this d phi. So let's just rewrite this a little bit. So let's move the phi x to the front. And then I consider psi of phi times the f hat bar of this phi d phi. And this one is, well, because your psi is inside L2, your f hat, the Fourier transform we just showed, is also inside L2. So when you take a product of two L2 functions, that's going to be inside L1. That's just Cauchy-Schwarz. So you have this function is an L1 function on the G hat, okay, the product of two L2 functions. So because it's inside L1, well, now you multiply an L1 function by the Harmonic measure, you get something inside the the measure space of the G hat. Okay, so this is inside M of G hat. Well, this one, if you remember, well, this one looks like the integral of all the characters against some measure on the M of G hat. Okay, this looks like the big phi of some measure. And we prove that this inverse Fourier transform has nice property. It's actually injective. So because this one is always equal to 0 for all, this is one is for all phi. Okay. All right. Because this integral is equal to 0 for all x inside your G, so basically, if you treat this as a measure in the measure space of G hat, and the phi of this function, the inverse Fourier transform of this function is equal to 0, well, so it just, because this inverse Fourier transform is injective, I have this measure has to be equal to 0. And if you have a measure, well, which is given by an L1 function multiplied by the Hart measure, well, you know the L1 function has to equal to 0. Okay, so this one implies that the psi times df hat bar d phi is going to be equal to 0, and that just only happens when phi times f check bar that's going to be equal to 0. Well, so essentially, this just proves that the psi, when you multiply against all the Fourier transform of these f, you get something 0. Well, the only chance it happens is that this psi is also equal to 0. Okay, so this finished the proof. And as a quick corollary, we have a slightly stronger result. We previously did the following. So if you recall, we actually showed that the G hat is an orthonormal set inside this L2 of G. Okay, so when you integrate the product of two of them, you get either 0 or 1. But if your G is compact, so if your G is compact, and you can normalize your G so that its measure is equals to 1, well, then, in fact, this orthonormal set is not only orthonormal set, it's in fact orthonormal basis. Okay, then this G hat is an orthonormal basis for the L2 of G. Okay. All right, so let's try to prove this fact. It's quite simple. So if you have a f inside the L2 of G hat, to show its orthonormal basis, I just need to show that if something is perpendicular to all of these functions in G hat, well, then what you have is must be a 0 function. So let's suppose f is perpendicular to all phi for phi inside G hat for all character. Okay, so what you have is that when you integrate this integral f and phi bar, and then let's say dx, so here's dx. So because you're inside the L2, so this one is going to be equal to 0. Okay, you're perpendicular, the inner product is 0. But the right-hand side is no other than the Fourier transform of f. Okay, so this is f hat of phi. But your f hat is equal to 0 for all phi. So in other words, your f hat is the 0 function. So f hat is going to be 0. Well, the f hat is going to be 0. Well, that's because your Fourier transform from L2 to L2 is isometric. That just means your f has to be equal to 0 as well by the Plancherel theorem. Okay, so in other words, the only thing that's perpendicular to all your characters is just the 0 function. So all the character is an orthonormal basis. Okay, so that's the end of the proof.